Could you take us through this paper predicting multi-codebook vector quantization indexes for knowledge distillation?
Okay, so a lot of times in machine learning, when we want to transfer some kind of something that's been learned, some kind of knowledge from one system to another, we'll compute embeddings like, high dimensional embeddings from the teacher system. And those might be embeddings for like frames of speech, or they could be words of text or ledgers of text or something. In this case, they're frames of speech. And we reduce them to a codebook index by using some kind of vector quantization or some related method. And then we predict the codebook index. And this paper is basically about instead of predicting one codebook index, to predict multiple different codebook indexes. But instead of doing this in a kind of ad hoc way, where we just train different codebooks with different parameters, we actually do it in a more optimized way, where we compute we jointly optimize several codebooks in a way that's optimized to predict the embeddings with minimum possible minimum distortion, which is like mean square difference. So basically, it's an optimal way of getting multiple codebooks, and the codebooks become more complementary because they're not trying to just represent the same information in different ways. So anyway, basically, the upshot of it is that it's better. It's better than using just one codebook index. I don't believe we've compared with kind of non-optimal, kind of ad hoc ways of getting codebook indexes. The problem is that there's a million ways to just get different codebooks, right? You can change the number of VQ indexes or whatever, and like we couldn't compare with every possible one, right? It's like trying to prove a negative. Anyway, so that's what it is. And I think we're doing distillation from like a Hubert type model to our model, and also from a large version of our model to a small version. And in general, it behaves pretty much as you would expect. This kind of distillation, it's useful to improve the system a little bit. And one of the advantages of doing it with codebook indexes, and so you also have another option that you can just predict the embedding produced by Hubert or whatever. But the problem is that that would make your training extremely slow, because big models are very slow to do the forward pass. So part of the idea of the codebook indexes is to have a very compact representation that you can just store to disk after computing it once, and then use it however many times you train in future. So yeah, I mean, I think it's a useful method. We do use it in our system. Sometimes we neglect to use it just because we didn't bother to set it up, but it's an easy way to get an improvement to most or pretty much any system. Okay, so this table 3, we're doing some kind of distillation from one system to another, and we're seeing how much it improves with different numbers of codebooks. And basically, with more codebooks, it's better. I don't think we universally find that it keeps getting better at such big numbers. I think sometimes 16 was better than 32 in my recollection, but in this instance, it looks like more is always better. These results are pretty much what you'd expect. This helps a lot more if you're training on a very small amount of data. When you have tons of data, the improvements are more modest, but it's still always useful. The way we get these code books there's this kind of iterative algorithm. It's a little bit like vector quantization, but with multiple code books. And you know, it's a little bit complicated. I don't remember all of the details, but basically you choose one code book and then you choose the other based on the remaining residual, and then you go back and optimize the first one again, and there's like a few iterations. And oh, it's actually even more complicated than that, because if you have a large number of code books, it kind of optimizes them in groups, and then it does some kind of n best thing to refine the possible choices. Basically, it tries to be as optimal as it can. All of this, I don't know how much difference it really makes to the final downstream task. It was done to optimize the Shannon distortion, which is just the mean squared error. And this table 1, it's showing the relative reconstruction loss. It's the same as the Shannon distortion, except we divide by the variance just to normalize it a bit. For Gaussian data, it's equivalent. And basically it's showing that we're pretty close to the optimal rate that you could theoretically get. The optimal distortion. So that on the bottom, the 0.760, it's in the same ballpark of the 0.707. I mean, it's much less than a factor of 2 difference, right? So the point is that, you know, it's not bad if you compare it with the theoretically optimal distortion you could get. The distortion rates for actual Hubert embeddings are much lower than this theoretical bound for Gaussian noise, because Hubert embeddings have a simpler distribution or a more predictable distribution, not simpler than Gaussian noise, so they're easier to reconstruct. So yeah, that's it.